In terms of the Coriolis effect, I highly recommend you watch two different videos. I posted them here. You can get them on a link via the PDF and get to them. It's not too hard to do. And I would show them here, but it really wrecks up my system when I am webcasting these videos and recording them in the cloud and trying to show YouTube at the same time. Doesn't work too well. So I want to let you know about that. The first video is probably the one that you're going to remember best, but I want you to only watch the first minute and 20 seconds of it. Okay? After a minute and 20 seconds, the science is incorrect. And while it presents a really great first section that you'll remember really well, the science and the directions that they're showing for the Coriolis effect are wrong, and they've been called out on it in YouTube, and the guy refuses to remake the video. So please only watch the first minute and 20 seconds. And on the second video, that's not as memorable, but it's correct science. So you can take a look at that as well. I am going to show you my analogy, and I hope that you'll go for those other two. So my analogy is Newark Airport and the moving sidewalks in Newark Airport. And I hope that you've all been there and you all know what I'm talking about, because they really speed you down these long corridors very well. So I want you to imagine that you've been painting a wall in Newark Airport that's right nearby the moving sidewalk, and you have paint all over your shoes, and you got to get this paint off your shoes. You got to get over to the bathroom and take off your booties and wipe down your shoes because they're a mess. So you decide that you have to get across the moving sidewalk, which is going from left to right here. So you are bound and determined to walk across the moving sidewalk directly to the bathroom that's over here. And so you go and you are bound and determined to walk across, and guess what happens? You don't get to walk across. Your wet booties show that you have actually been deflected off to the right with the direction that the moving sidewalk was going in. There was no way for you to go across. You were being moved with the direction. You were being changed in that direction by the Coriolis effect. And what this is in response to is the counterclockwise direction of the rotation of the Earth. And you might say, I'm at the equator, and I want to walk up to Mexico north of them, and I'm going to walk directly up to Mexico north. And you head out in your direction due north, and you do not get to Mexico because your footsteps get deflected to the right in with the counterclockwise direction of the Earth's rotation. So this is an effect that can also be moved into a cloud that happens to convect off of the equator and wants to go north to the North Pole, does not get to the North Pole. The cloud is deflected off to the right, and the cloud moves off to the North Atlantic when it's deflected off to the right. This impacts our global circulation, and that's what I want to explore a little bit more. So when it impacts our global circulation, it impacts many things that go to the north or to the east or to the south or to the west. In the northern hemisphere, all of those objects that are moving and being deflected off to the right, especially when they are in the upper atmosphere where there is very little friction, and especially when they are traveling at very high speeds. I mentioned to you about the World War I artillery by the Germans and how they would fire at the French, and they would be firing from a location that, well, let's say they're off to the east, and they're firing into France to the west, and guess what? Nothing made it to France. It landed a few miles off its target because the artillery deflected to the right. And so it actually deflected if they were on an eastern position firing to the west, it deflected a few miles to the north. Right? The impact this has is that your jet airliner, which travels at very high altitudes, at very high speeds, actually has to correct for the Coriolis effect and has to correct by computer to make sure that it doesn't end up, instead of going from San Francisco to New York, it doesn't end up in Miami, because it would normally deflect to the right if it's going from its western location to its eastern location, and it deflects to the right, it's going to deflect to the south. Computers now counteract that and adjust the direction of the plane. Interestingly enough, to make the first flight across the Atlantic, Lindbergh was very aware. This was 1927. He was aware of the Coriolis effect. It was post-World War I. And he flew very close to the Earth at a slower speed to minimize the impact of the Coriolis effect, which takes place when you are at high speeds at very low friction, at very close to the ocean. A lot of friction, a lot of, and when I say a lot of friction, I'm talking about the friction of the water vapor right off the ocean. It actually impacts flight, and it's also a slower rate of speed in that area. So he didn't notice the Coriolis effect very much, but he did counteract for it a bit. So when we talk about clouds in Coriolis effect, we're also talking about clouds moving in the atmosphere, and we're talking about ocean currents moving as well. Now you might say the ocean currents are not at high altitudes, but the ocean currents actually have a flow to them that is really has really low friction when you are in the ocean rather than just above the ocean. And so you'll note here that the Gulf Stream would normally come from the equator and try to head north, but guess what? It deflects to the right. And look at this. The Canary Islands are impacted by a current that comes from the poles, from the north, and tries to go south, but it gets deflected to the right and goes west. So this Coriolis effect impacts planes and artillery and ocean currents and winds. And so you're seeing the ocean currents, which definitely impact our atmosphere, and the winds as well. This is it's called a fake force, it's called an effect, it's called an apparent force. It's due to the rotation of the Earth, the counterclockwise rotation of the Earth. And in the northern hemisphere, it deflects to the right, and in the southern hemisphere, it deflects to the left. It's very cool. You'll find more information out about that in the videos, and I have a video where I did a lab demo that you can look at with the balloon as well. I highly recommend you look at it so you can convince yourself of this. This happens over long distances, for instance, artillery and planes and winds and ocean currents has no impact on the speed of any of these objects. It just impacts the direction of them. So only 1/2 of the vector. The stronger, in atmospheric science, the stronger the speed of the wind, the greater the deflection to the right in the northern hemisphere. And the amount of that deflection is not only impacted by the speed, it's also impacted by the altitude. You're facing a higher Coriolis effect at higher altitudes, and it is also present at latitudes. For instance, the farther north you are, the slower the counterclockwise rotation, the more the impact of the Coriolis effect. The closer to the equator you are, the less the impact of the Coriolis effect. That's in the videos too. Like I said, long distances and high speeds. That is the reason why when we look at high pressure to low pressure, we see a deflection to the right. And when we look at high pressure 1012 to low pressure, let me get in here, high pressure to low pressure 1012 to 1008, we see a deflection to the right. All right. Now we're going to talk about the curve on those deflections as well, and I think that is in the next. No, we're going to talk about it right here. These deflections also have a curve to them. Like you might say, that's going from high pressure to low pressure, and then it's being deflected to the right, but it's also heading out a bit. And guess what? Centripetal, centrifugal force is also involved there. So the same thing that you notice on the tilt-a-wheel, that when the speeds increase, you get blasted off to the right away from the center. The same thing you're noting here. This has kind of a curve to it because of the centrifugal force that's noted from, especially when you have tight gradients and higher speeds. So that centrifugal force combines with the Coriolis force to tilt to the right on a curve, and it actually competes against the frictional drag that's trying to slow down the wind. So we'll go over that a bit. And I wanted to talk about the lows as well. Like you see that curve in there. That's not just a deflection to the right. It's kind of a curve in. Yes, it is. And it's a curve in with centripetal force when you lean into a curve. So when you are moving into a center of pressure, you are leaning in and you're impacted by centripetal force, which causes you to curve in a bit more. This combines with Coriolis and moves you into the right, and it combines in with the frictional drag because everything's slowing down when you're moving in, and you'll notice a bit more of that drag in on that. I hope that helps you out. You can read up a bit more about that, and you just learned a lot about physical forces right there. Take care.